Redox reactions, short for reduction-oxidation reactions, are a fundamental class of chemical reactions where electrons are transferred between atoms, ions, or molecules. In a redox reaction, one substance loses electrons while another gains them. The substance that loses electrons is said to be oxidized, and the substance that gains electrons is reduced. The concept of redox reactions is central to understanding many chemical processes, from simple reactions like rusting to complex biological functions like cellular respiration. The key feature of any redox reaction is the transfer of electrons. This transfer alters the oxidation states of the involved substances. Oxidation involves the loss of electrons, which results in an increase in the oxidation state of the atom or ion. Conversely, reduction involves the gain of electrons, leading to a decrease in oxidation state. For instance, in the reaction between sodium Na and chlorine Cl2 to form sodium chloride NaCl, sodium atoms lose electrons, are oxidized, to become Na-positive ions, while chlorine atoms gain electrons, are reduced, to form Cl-negative ions. This electron transfer makes the reaction a redox process. Displacement reactions are a specific type of redox reaction where a more reactive element displaces a less reactive one from a compound. In these reactions, the more reactive metal loses electrons, is oxidized, while the less reactive metal gains electrons, is reduced. For example, when zinc metal is placed in a solution of copper sulfate CuSO4, zinc displaces copper from the solution because zinc is more reactive. The reaction can be represented as shown on the screen. In this reaction, zinc atoms lose electrons and are oxidized to form zinc ions Zn² positive, while copper ions Cu² positive in the solution gain electrons and are reduced to copper metal. The zinc displaces copper from the copper sulfate, demonstrating how displacement reactions inherently involve redox processes. Ionic equations are used to simplify the representation of redox reactions, focusing only on the components directly involved in the electron transfer. These equations omit the spectator ions, those that do not participate in the redox change, allowing us to see the useful bits of the reaction more clearly. For example, the ionic equation for the reaction between zinc and copper sulfate can be written as shown on the screen. In this representation, the zinc atoms lose 2 electrons to become zinc ions, and the copper ions gain those electrons to become copper metal. This shows the essential redox changes without the distraction of the sulfate ions, which do not change during the reaction. Redox reactions are pervasive in both industrial and natural processes. They are involved in everything from the generation of energy in batteries to the metabolic processes in living organisms. Understanding redox reactions, including the transfer of electrons, the role of displacement reactions, and the use of ionic equations, is crucial for grasping the mechanisms behind many chemical phenomena.